So we've discussed how basically you can combine all the individual rules, Boyle's and Charles and Gay-Lussac, to make one big rule, and this is all you really have to use is this combined gas law. So the combined gas law will take the pressure and the volume and the temperature in one situation and equate it to the pressure, volume, and temperature of a second situation. So this only works for like bubbles or balloons or tires or any situation where the amount of gas is staying constant in two different situations. And the key here is um, if something is constant, then you get to drop it out of this equation. So the key is going to be looking for these units. When you see liters, you know you have volume. When you see Kelvin or degrees Celsius, you know you have temperature. And then unfortunately, because of atmospheres, uh, kilopascals, millimeters of mercury, torr, psi, all of those are pressures. That's sort of the harder one to figure out. But basically, if you got your liters and you got your, these two should be pretty obvious to you. Volume is liters and temperature is degrees Celsius. Pressure is a little bit more difficult because there's so many things. But let's get into it a little bit. So here we have a situation where an aerosol container is our um, so that is our container. And as a container, it holds gas, right? So we have this situation here, ATM. ATM is telling you pressure, and then degrees Celsius is telling you temperature. And since they're the first ones listed, we can call them P1 and T1. Now we're looking through, it says it's thrown into a furnace. Here's another degrees Celsius temperature. Oops. So that's going to be T2. Easy there. So that's going to be T2. First, I need an eraser, I guess. There you go. That's going to be T2. All right. And you're trying to figure out what pressure will this can be, and will it be around 4 atmospheres? So you're looking for P2. And that's just a matter of looking at the question. Now, what you'll notice is not here, there is no liters. And since there's no liters, we can drop the volume from our thing. So there's no liters. So we're going to drop volume. So in our situation where we're setting up P1, V1, and T1, our T is the temperature, but we have to put it in Kelvin because everything needs to be in Kelvin. That did not stand out like I wanted. Let's try it again in yellow. Everything wants to be in Kelvin. All right, it needs to be in Kelvin. So that's why we added 273. You may recall that that's what you do to turn things into Kelvin. Our volume is constant. Our pressure, too, is what we're looking for. Is it greater than or less than 4 atmospheres? Our volume is again dropping out because it's constant. So we're dropping that out and we're dropping that out. And then our temperature, we add 273 again. So now we're just going to plug this into our equation. And our equation is P1V1 over T1 equals P2V2 over T2. And since the volume is constant, we cross that one off. So we're not going to deal with that. And we just get P1 over T1 equals P2 over D2. And that's not doing anything too crazy because actually it said in here, volume is constant, right? So that's basically P1 over T1 equals. So we got the same thing, only we used all the information provided to us in the problem. All right. So our P1 is 1.5 atmospheres. So we get the 1.5 atmospheres, and we're going to divide it by the temperature, which is 298 Kelvin, and that's going to equal our P2, which is what we don't know. So P2, or you can use an X if you like X's, and then our T2 is a 723 Kelvin. Now you can do one of two things. You can cross multiply, right? Because there's an equal sign here. You can either cross multiply or you can just figure things out with numbers and algebra. So if I'm going to take the 1.5 and divide it by 298, I get 0.00503. So the green number becomes 0.00503, and then that's going to equal P2 divided by 723 Kelvin. So to isolate my x, I need to multiply 723 on both sides. And that's how I get my answer. Oops. Enter. All right, so I get 3.63. So P2 equals 3.63 atmospheres. The pressure here has to resemble what went in. And 3.63 is still less than 4, so it will not burst, answering the question. All right, so here's another example. We're looking for our constant. So we have this here, liters. We talked about how liters is a volume. And we have degrees Celsius. Hopefully you know that's a temperature. And then what volume? It's looking for a volume. The what statement, right? What is talking about volume. So that's a V2. And then 55 degrees Celsius is a T2. So our constant, the thing that we're not seeing anywhere, is pressure. So pressure is constant. And since pressure is constant, we can eliminate it from our equation. So here's how things line up. Our P1 is a constant. Our V1 in the first case is the 0.750 liters. Our V2 is what we're looking for. Our T1, we have to add 273 to 22 degrees Celsius. And our T2, we have to add 273 to 55 degrees Celsius. So what we're going to do then is, so it's P1 V1 over T1 equals P2 V2 over T2. And in this case, because pressure is constant, we're going to cross off our pressures. We're going to cross off our pressures. So it's just V1 over T1 equals V2 over T2. So our V1 is 0.750, and our T1 is the 295 Kelvin. And then our V2 is the question mark, right? So that's our variable. And our T2 is the 328 Kelvin. So again, you can cross multiply or you can turn that into a number and divide. This time I'll cross multiply just so you have an example of that. So 7.75 times 328, geez, is 246. So we got 246 is equal to 295 times V2 is 295 V2. So to isolate our variable, we want to both sides divide by 295. And we get 246 divided by 295. V2 equals 0.883. So our volume, 0.833. The units of that are the same units that went in for volume. So liters went in, so liters have to come out. All right. So last example with a constant. Neon is occupying, here's our liters, right? It's milliliters this time, but it still says liters. So that's telling us it's a volume. And then here's atmospheres. Atmospheres is not degrees Celsius, right? So this has to be a pressure. We'll call them both 1. And then at constant temperature, it even says constant temperature. So temperature is going to be constant and eliminated. And the other number we have with the unit is ATM. So ATM is telling us that's a P, and it's the second one. We're looking for the volume. The what statement is looking for volume. So V2 is our question mark. So we set that up. Our temperature is a constant. It said so. It wasn't mentioned. There's no degrees Celsius in this problem. There's no Kelvin in this problem. So that's what gets it knocked out. Our P1, our P2 we've established, our V1, our V2 is going to come out in the same units as what goes in. So if the first one has milliliters, it comes out as milliliters. All right. And then this first one here has atmospheres, and this one has to be in atmospheres. So P1 V1 over T1 equals P2 V2 over T2. We're going to cross off those temperatures. because they're constant, right? So it's just P1 V1 equals P2 V2. So now we're going to substitute in for P1 the 0.971, and we're going to sub in for V1 the 72.5, and that's going to equal, we're going to sub in for P2 the 1.40, and our V2 is our question mark, so we're going to leave that as a variable. Multiply the green things, 0.971 times 72.5 is 70.39. So this is, I think I need to make that green. Yes. So 70.39 is equal to 1.40 V2. So in order to isolate this variable, we need to divide by 1.40 on both sides. And we get 50.3. So V2 equals 50.3, and the units of that are going to be the milliliters because the milliliters is what went in. So the milliliters is coming out. This would have worked just as well if we turned everything into liters. Our answer would have been 0.0503 liters, which is fine. All right, so then moving on to when everything's there and there are no constants, this may be a little easier or maybe it's a little harder. You just have to figure out what everything is. Here's 3 atmospheres. Atmospheres is a measurement of pressure. Kelvin is a measurement of temperature. And liters is the measurement of volume. So that's the first situation before it gets heated. A gas has this pressure, this temperature, and this volume. Then it is heated. So our second situation, changing our colors, here's our T2, and here's our atmosphere is telling us P2, and the what statement points to a volume, so the V2 is the question mark. So if we lay all that out, P1 is the 3 atmospheres, V1 is the 318 liters, it's already in liters. Our temperature is in Kelvin, so we don't have to convert that. Our second situation, 2.5 atmospheres. Our volume we don't know, and our temperature is 323. So our P1 V1 over T1 equals P2 V2 over T2. We'll have nothing eliminated. It's all there. So we're just going to substitute in for P1 the 3 atmospheres. For V1, it's 318 liters. So I'm just substituting in what's there, and the T1, I'm going to substitute the 293. And that's going to equal on the other side, our P2 is the 2.5 atmospheres. Our V2 is what we're looking for. That'll be in liters because this is in liters when we're done. And the 323 Kelvin, already in Kelvin, we didn't need to do anything with that. So now this is algebra. And with the algebra, you can turn this into a number easy enough. 3 times 318 is 954, and then divide that by 293. So our green number becomes 3.255. It's 3.255. After you turn all that, actually 256 even. And then our blue numbers, we can divide 2.5 by 323, and we get 0.00774, and then the V2. So this V2 is our variable. That's the thing we need to get alone. So we want to get rid of this and put it over here. So 3.256 divided by 0.00774 gives us 420. So the V2 equals 420. 420 has the units of liters because the other thing is liters. So it's actually 421 because it's 420.6. Those are both fine. All right. One more of these. STP. Now, this is the annoying thing, and I put it back here because that wasn't smart. But STP. So standard temperature and pressure. The standard for temperature is 0 degrees Celsius, which is 273 Kelvin. The pressures are all this nonsense. Look at all this stuff. and you got to just pick the one that's useful. So there's ATM, there's KPA, there's millimeters of mercury, there's PSI, all everything's here. So when we're doing this, all right, we have a volume. Here's our liters, so that's our volume. STP, we know the Kelvin is 273. That's our T1. What we don't know is our P1 yet because we got to keep reading. So we keep reading, and then the second situation this gas is in, the new situation, is torr. So we need to use that pressure in torr. So here's our P2. Liters is telling us that's a volume. The what statement is looking for temperature. So that's our T2. So our P1, we want to use torr, and the one that's in torr, give all that, is here, 760 millimeters of mercury or torr. They're the same unit. Thank science. All right, so here we go. So our P1 is 760 torr because it's at standard temperature and pressure. Our V1 is the 895. Our T1 is the standard temperature, which is 273. Our P2 is the given 1277. Our V2 is the 574 liters. Our T2 is the what statement. The what is pointing to temperature. So when we set all this up with a P1 V1 over T1 equals P2 V2 over T2, we just start filling in for everything. So our P1 is 760. Our V1 is 895. Our T1 is 273. And that's going to equal our P2 is 1277. Our V2 is 574. And our T2 is what we're looking for. So again, we can turn that green stuff into a number, 760 times 895 divided by 273. So this becomes 2491. You can say 92 even. And then our other number, 1277 times 574 is 732998 divided by T2. So now we need to get that T2 by itself. It's right now in the denominator. So we want to multiply both sides by T2 to get it out of the denominator. And then since we have 2492 T2 will equal 732998. We want to divide both sides now by the number so we can isolate our x, which is the t. So we're going to divide by that, and on what we do to one side, we do the other. So T2 is going to equal that 732998 divided by 2492, which is 294. So T2 equals 294. It's a temperature, so the units of that are